Hello, I'm Matthew Rodriguez, and today I'm going to be presenting work that I did with my advisor, Michael Spear, on implementing software transactional memory in the C++ memory model. First, a little bit of background. Transactional memory, or TM, is a concurrency control mechanism. There's several different types of transactional memory. There's STM, software, HTM, which is implemented in hardware, and hybrid TM, which uses both software and hardware. Rather than using traditional concurrency objects such as locks, the programmer denotes blocks of code as being atomic. After that, the system handles the concurrency. The goal of TM is to maximize concurrency while ensuring correctness. For example, a very simple but very inefficient but correct implementation of TM would be just have a single global lock and acquire it at the beginning of every atomic block of code or transaction and releasing it at the end. However, TM seeks to do more than that. For example, if you've got two transactions that don't even access the same variables, then there's no reason why they can't happen in parallel. In our work, we observe that the C++ memory model makes some design decisions that pose unexpected challenges for STM implementations. When two or more threads access the same variable at the same time, all threads must regard it as an atomic variable, or else it is a data race. Program behavior is undefined in the event of a data race. Now, undefined doesn't mean like, oh, maybe A will happen before B, or B will happen before A. No, undefined means undefined. Now, does this matter in the real world? You could say like, okay, maybe the C++ memory model says this is undefined, but in the real world, a sensibly implemented compiler like GCC will do something that makes sense. Well, the impetus for this work was a non-obvious bug that arose in other work we were doing, resulting from what we thought was an acceptable use of sequence locks on variables that were not declared atomic. It took us a while to track down the code, and that eventually led to this work where we realized that the bug in our code applied to TM implementations as well. So the conclusion of this is that the most natural seeming implementation of STM has data races in it. Fortunately, for the normal use case, there is a trivial workaround. It just involves marking the variables that you share as atomic, and it has a minimal performance impact. Unfortunately, for privatization, a design pattern that is used in some TM implementations, our work uncovers a serious scaling issue with major impact on STM and hybrid TM designs. So how do we address the first problem I discussed, the data races in the normal case? To explain that, let's look at this code. This code depicts a simplified STM based on ownership records, or ORECs for short, and an undo logging based STM. In this example, thread R is the reader and thread W is the writer. So this code is correct, but without these two cast to atomic, this code would constitute a data race. The fact that the reader is going to detect the race and avoid using the red value is irrelevant. According to the C++ model, there's no stipulation about, oh, it's okay if you don't use the variable. No, it just says, if there's a data race, behavior is undefined. So this example presents an undo logging implementation, but redo logging has a similar issue in its commit phase. Another thing to note here is that the reads from R4 to 6 cannot use a relaxed memory order. Those acquire fences are necessary to prevent the compiler from reordering the code. So we might want to use a relaxed fence to get for the performance benefits, but unfortunately we can't. Next, we discuss privatization. So this code depicts an attempt to implement privatization using TM. The previous code was correct because of the casts that we included. This code is incorrect, and let's explain why. So in this code, thread P is trying to privatize the shared variable shared data so that thread T cannot see it. It wants to put it in a state where it can access it exclusively. Prior work by other researchers has uncovered two braces in this code. Suppose that line P7 occurs between T5 and when T reaches its commit phase. The first race, which occurs when using a redo logging based TM, occurs when T commits. In that case, P7 will read the stale data. This is because T needs to serialize before P, but P is reading the old data from before when T reached its commit phase and actually wrote the value to the shared data. In the second case, with an undo logging-based STM, we suppose that T aborts. In this case, P7 will read the value written by the aborted transaction of T, which is also an invalid value for it to have seen. In addition to these two existing races, we observe a third race condition. The fact that T5 can happen concurrently with P7 is necessarily a data race, even if races 1 and 2 are avoided. Again, this is just because of the way the C++ memory model is defined. If you have concurrent accesses to a variable, and one of them is not atomic, then it's a race. So T may be treating it as an atomic variable because it's at a point in time where it expects it to be shared and written by other threads, but P has privatized it, so it's not using it as an atomic variable. Now, you might say, oh, there's a simple solution to this. We just make P atomic. Well, this is an unsatisfactory solution. We want shared data to be private to thread P. That's what we expect from privatization. And in a less trivial example than this one, where we're just working on a shared integer, how much data would we need to make atomic? Could possibly be all the data in the program. So how do we solve these privatization bugs? The first solution is quiescence, and this is the simple form of quiescence. Any committing transaction must wait for all other transactions to commit and clean up. This ensures that T's transaction finishes and cleans up before P exits and begins executing post-transaction code. There is also an improved version of quiescence, which only works for redo-based STM. This allows P to resume as soon as it knows that T's transaction will have to abort. It saves a little bit of time. The last solution is to serialize all commits. This is the most ambitious solution and can be the most performant when it works, but it only works for redo-based STM. In this case, every transaction validates on every commit. So if any transaction commits, every other transaction has to validate. And if it discovers that it has a conflict on some variable, then it will abort immediately rather than waiting for the end. This resolves the first race node in the previous slide. However, we note that solution C, which involves serializing all commits, is incorrect. A data race, as defined by the C++ memory model, still occurs. Solution 2, with the improved quiescence, is sometimes incorrect. In particular, it's incorrect for TMs that use value-based validation, where the TM checks the value instead of the OREC or other metadata. This means that hybrid no-rec and reduced hardware no-rec are incorrect as described. So now we're going to look at some charts that show the impact of our fix on the code. In this charts, you're about to see the y-axis is time and lower is better. We note that the impact of using atomics is minimal, but the impact on privatization is significant. So in this slide, fixed means we apply our fix that makes everything atomic. Incorrect is the previous version of the code where the shared variables were not atomic. Eager is a undo-based STM, and lazy is a redo-based STM. And no-rec is an STM with no ownership records, and fixed refers to our version where we remove quiescence and use atomic variables. No priv means we use the incorrect version of privatization, but we do use atomic variables, and incorrect means everything about it is wrong. It's using the wrong version of privatization, and it's not using atomic variables. As we can see here, the impact of the use of atomics is not significant, but unfortunately, the blue line representing the fixed version of no-rec is significantly slower, and we see the same thing on this page as well. In conclusion, the C++ has a surprise in it. It doesn't work the way many people think it does. C++ doesn't actually allow a correct implementation as it is today. Casting to state atomic isn't really correct, but it's close enough, and if you look at the emitted assembly, then it produces the correct code. We need atomic ref, which is coming in C++ 20. The current solution has minimal impact, and the impact of atomic ref will be minimal as well. But unfortunately, the best approaches to privatization are impossible in C++. Thank you very much for your time.